Welcome to Mydreamsacademy.
Welcome to online tutorial offered by Mydreamsacademy. My name is T. Benjamin Sunday, your chemistry tutor. Of course, you know me by Massacre. We are here to offer, as usual, chemistry today on the topic theory of dilute solution. Please always remember to subscribe to our YouTube channel. All right, class, just like our topic today is theory of dilute solutions. Theory of dilute solutions. Now, that is our main topic. But in this topic, we are going to be considering colligative properties of dilute solutions, Raoult's law of ideal solution, and then Vant Hoff's theory of dilute solutions. Now, to start with, let's look at what is colligative property. We said that a colligative property is a property which depends only on the number of particles present in solution. Number of particles present in solution. That is what a colligative property is. Now, we are saying that the essential feature of a colligative property is that it depends only on the number of particles present. Now, what we are saying here is that a colligative property, just like this word colligative means together. Together. So we're talking about property of a solution that will depend on the number of particles that are together in a solution. Not necessarily on the type of particle or whether the particle is reactive or not reactive. Our interest is on the number of the particles that are present in solution. Not on the type of the particle, not on the type of solute, but on the type of particle. Now, of course, our main target here is on solids, solutions formed by dissolving solids in liquids. That is why here we have we're talking about dilute solutions of solids. Of course, you know, solids may be, of course, a solid may be solid or any that, but our interest is on solids dissolving liquid solvents. Now, there are four colligative properties we're going to consider here. One is lowering of vapor pressure. Two is elevation of the boiling point. And now three is depression of freezing point, and the fourth one is osmotic pressure. All right, so just like we are talking about the number of colligative properties, right? Now, I've told you that colligative properties, there are four colligative properties of dilute solution of utmost importance that we must know. Then I've also told you that colligative properties of solution actually depends on number of dissolved particles. Now, let's look at them one by one. But before that time, one thing you must know very well in class is that all the colligative properties are related to each other. And also, they provide important information, or they provide methods that will be used to measure molar mass. So they are very, very essential, right? Now, let's pick the first one, which is lowering of the vapor pressure. Now, when we talk about vapor pressure of a liquid, what actually causes vapor pressure of a liquid? You know, class, that when you keep a liquid in a container, some of the molecules might get agitated, the energy will increase, and then they start to escape through the surface of the liquid. That is evaporation. Now, but eventually, if you add anything like solute into this solvent, you see that the particles of the solute will block some of the solvent molecules, preventing them from escaping, from moving. In that case, we say that the vapor pressure has been reduced, because the rate at which the solvent molecules escape from the surface has been reduced. Automatically, the vapor pressure has been reduced. Now, as a result of this, we say that the vapor pressure of a liquid is directly proportional. The vapor pressure lowering of a liquid is directly proportional to the mole fraction of solutes in the solution. Now, class, there's something I want you to know here. What I want you to know here, and you have to be careful about it, is that, for example, now, if I get pure water, and I get water in which salt or sugar has been dissolved in it, class, which one do you think we have higher vapor pressure? Which one? You are correct. The answer is pure water will have higher vapor pressure, because that water that contains salt, which is a solution, what we find out there is that the salt particles is blocking escape of some water molecules. As a result, you see that vapor pressure has been reduced. Now, pure liquid always have higher vapor pressure than impure liquid. Very, very important. You must note that. So now, we say that the amount of solute in a solution determines the lowering of vapor pressure. And that is, remember what we talk about colligative property that depends on number of particles dissolved. So if you dissolve more particles, more solute particle in a solution, then get ready to see more lowering of vapor pressure. Get ready to see more lowering. That's what we're talking about. Now let's talk about Raoult law of dilute solution. The Raoult law states that the relative lowering of vapor pressure of a solution is directly proportional to the mole fraction of solutes in that very solution. But you have to be very careful. Of course, Raoult law is applicable only to dilute solution, not just dilute solution, but ideal solution. Now, why I made mention of solution of non-electrolyte is that non-electrolyte, extremely dilute solution of non-electrolyte approach ideality. So they behave like ideal solution. So it is, in real sense, it is only a dilute solution or extremely dilute solution of non-electrolyte that can behave or that can obey Raoult law. And how can you get extremely dilute solution? You keep on diluting a solution until the concentration is zero, which is almost practically impossible. Keep on diluting until the solution is said to have zero concentration. At that case, you say that the solution has been infinitely diluted. That is when Raoult law will be obeyed. Now, of course, we have mathematical expression for it, but that is not our scope. Now, remember, our aim is to make sure that you pass your screening and your jam very, very well. Okay? All right. Of class, we have been talking about colligative properties. Now, let's look at boiling point elevation. Boiling point elevation. Now, when a liquid is heated, as you are heating a liquid, you see that you begin to see bubbles. The molecules is rising. And as it's rising, some of them will be escaping through the surface of the liquid. Now, as the liquid is rising to the surface, molecules is rising to the surface, you see that the vapor pressure of the liquid is increasing. Now, a time will come when the vapor pressure becomes equal to the pressure of air around that very liquid, the free surface of the liquid. That is when you now say that the liquid is now saturated. And once that happens, the liquid starts to boil. You will see many bubbles inside the liquid. Now, that is when you now say that the liquid cannot boil. Now, class, let me tell you this. You talk about normal boiling point, because we also have normal boiling point. We have seen that boiling point depends on vapor pressure of the liquid. So as the vapor pressure of the liquid increases or decreases, it will also affect boiling point. Now, whenever vapor pressure of a liquid is exactly 1 atm, and liquid boils at that 1 atmospheric pressure, that very boiling point obtained is called normal boiling point. And the normal boiling point of pure water is 100 degrees Celsius. Please take note of it. Now, class, let me tell you something. You must know that a solution will boil after a pure liquid has started boiling. In other words, salt water or seawater will not boil faster because the vapor pressure is lower than that of pure water, right? So you have to take note of that. Then another thing worth noting is that a pure liquid, like we said, will boil faster than impure liquid, but that depends on the nature of impurity in that liquid. If the solution contains a non-volatile solute, then the liquid will boil before it. But if the liquid contains volatile solutes, maybe something like acid, the solution will boil faster. Please, I take it again. Pure liquid will boil faster than a solution that contains non-volatile solute. And the same pure liquid will not boil faster. It will boil later than a liquid that contains a volatile solute. Please take note of that. So we have normal boiling point, which is boiling point when the vapor pressure of a liquid is exactly 180 em. That 180 means 1 atmosphere. Now, boiling point elevation is directly proportional to molality of a solution. What is molality? Molality of a solution simply means number of moles of solute dissolved in exactly 1000 gram or 1 kg of that very solvent we are using, the solvent in question. And remember, please don't misunderstand molality with molarity. We have molarity. Molarity simply means number of moles of solute in 1 dm cube of solution. 1 dm cube, please take note. 1 dm cube. Molarity is 1 kg of solvent. Number of moles of solute in 1 kg of solvent. And that is what we are using here. Okay, not molarity, right? So that is it. And like we said, if you look at the expressions here on the board, right, that is the relationship between boiling point elevation and molality of solution. As you can see it, molality of solution is directly proportional to boiling point elevation, right? Or you say boiling point elevation is directly proportional to molality of solution. So look at the mathematical expression on that, right? Very important to memorize the bit. Of course, why we're not going to perform calculation here is because it's not within our scope. They will not ask you that in the exam, right? Very important. And as you can see, that boiling point, this symbol represents boiling point elevation, right? Boiling point elevation. This one represents boiling point of solution. This one represents boiling point of pure solvent. As you can see, boiling point of solution is greater than boiling point of pure solvent, right? Please, you take note of that. So here, a pure liquid boils faster than a solution containing non-volatile solute. Very important, take note of it. And that is why you see that pure sample of water will boil faster than sea water, okay? So very important to take note of that, please. Now let's look at freezing point depression. Class, when we talk about depression, we talk about going down, lowering. So what we are trying to say is that freezing point of a solution will be lower than freezing points of pure solvent, pure liquid. So by adding a non-volatile solute into a pure liquid, you are lowering or depressing the freezing point of that very liquid by adding a salt in it. For example, when you add a salt or dissolve a salt in water, that salt, while dissolving, will be extracting heat from the water. It will be extracting heat from the water, thereby cooling the water, right? Now, by cooling the water now, it has cooled the water below the normal temperature. Now, when you put such solution now in freezer and put pure water in freezer, you see that you're going to find out that that pure water will freeze faster. But let me illustrate this. For example, normal freezing point of water is 0 degrees Celsius. But salt water will freeze at temperature below 0 at about 20 degrees Celsius. Remember that liquid water, the temperature is at 25. That's normal, what you call room temperature. So the cooling begins from this. So as liquid water is cooling, it is cooling from 25 down to 0. If the water is pure, it freezes. It becomes frozen. Now, if the water is impure, if it contains impurity like dissolved salt, the freezing will happen below 0, no longer at 0 again. So 0 is called normal freezing point. Class, it's also possible for water to freeze at temperature above 0, depending on the amount of salt or amount of non-volatile solid that it contains. But the truth is that as you are adding more, dissolving more salt in water, you are lowering the freezing point. You are lowering the freezing point. I repeat, you are lowering the freezing point. But a time will come when the concentration of salt becomes excessive, becomes maximum. That is called eutectic concentration. Look at it here. Eutectic concentration. That's the maximum concentration of solute in a solution. At that point, the freezing point becomes minimum. We call that eutectic temperature. Okay, eutectic temperature. If you now increase the amount of salt, if you increase the amount of dissolved salt particles beyond that maximum value, eutectic concentration, please note that instead of the freezing point to continue to reduce, it will now start rising again. That is why you must ensure that you don't exceed the maximum concentration that the solution should contain. Okay? So freezing point depression is directly proportional to lowering of vapor pressure. The more you lower the vapor pressure, the more you depress the freezing point. Right? So in summary, always remember that a pure liquid freezes faster than a solution that contains non-volatile solid dissolved in it. Such as if you compare pure water and seawater, you see that pure water will freeze faster compared to the rate at which seawater will freeze. Okay, very important that we must know. All right, so let's now talk about we have been talking about colligative properties of a solution that contains non-volatile solid. Now, a non-volatile solid could be an electrolyte. It can also not be an electrolyte. It may be a non-electrolyte. I want you to know that sugar is a non-electrolyte. But sodium chloride is an electrolyte. Now, what are we trying to say? We're trying to say that colligative effect produced by electrolyte is always greater than that produced by a non-electrolyte of the same molality. What am I trying to say? Watch this. You know very well that 1 mole of a solute is equivalent to molar mass of the solute. Is equivalent to molar mass of the solute, right? Now, what does that mean? It means that 1 mole of glucose is equivalent to 180 grams of glucose. Since molar mass of glucose is 180 grams per mole, Watch again. 1 mole of sodium chloride is equivalent to 58.5 gram of sodium chloride. Right? Now, what am I trying to say here? We say that the colligative effect produced by electrolytes is always greater than that produced by a non-electrolyte. If I measure 180 gram of glucose and dissolve it in pure water, remember, boiling point, normal boiling point of pure water is 100 degrees Celsius. And then there is what we call ebullioscopic constant, which is molar elevation constant. What does that mean? It simply means that the rise, how much boiling point of a solution will rise when you dissolve 1 mole of a solute in it. For example, the molar elevation constant or the ebullioscopic constant or the boiling point constant of pure water is 0.52 degrees Celsius. What does that mean? It means that if you dissolve 180 gram of glucose in pure water, the boiling point of the solution will be 100.52. Okay? Now, which means normal boiling point of water is 100. The solution is now 100.52, right? So, which means this boiling point of the solution is greater than boiling point of pure water. But if it is a salt, like electrolyte, sodium chloride, the boiling point may not be this, it may be greater than 100.52. What that means is that we're trying to say that the colligative effect produced by electrolyte is always greater than that produced by non-electrolyte. Even though that by dissolving 180 gram of glucose is 1 mole that you have dissolved, by dissolving 58.5 gram of sodium chloride is also 1 mole you have dissolved. But two of them are not going to give you the same boiling point. The reason is that sodium chloride is an electrolyte, a strong electrolyte. Glucose is a non-electrolyte because the molecules will not ionize. Okay, it will remain as molecules when you place it in water. Now we have what we call heat-up factor. Sorry, not heat-up factor anyway. Vant Hoff factor. Heat-up factor is when you're talking about relative velocities of ions of electrolyte. Now, Vant Hoff factor is simply the ratio of colligative effect of electrolyte to the colligative effect of non-electrolytes of the same molality, the same concentration. Like now, if I want to measure the colligative effects, that is the boiling point elevation, how much 180 gram of glucose will raise boiling point of water, and how much 58.5 gram of sodium chloride will raise boiling point of water. If I measure the boiling point elevation of this and that of this one, and I divide that obtained with sodium chloride by that obtained by glucose, I will have what we call Vant Hoff factor of sodium chloride. Okay? And now, to shock you, the Vant Hoff factor of sodium chloride, an extremely dilution of sodium chloride is 2. Let me show you this. So, for if that is very dilute solution, for very dilute solution of sodium chloride in water, Vant Hoff factor equals 2. What does that mean? Look at it. Sodium chloride is NaCl, is an ionic compound. So if a solution of sodium chloride is extremely diluted, very diluted, it means that the ions have completely separated from each other. They are no longer attracting each other. So the ions are now free to move about. No interaction between them. So this is one ion. Some of the 2 ions, that is 2. Okay, so that's why the Vant Hoff factor of sodium chloride is 2. Now, in case you ask for extreme dilution of calcium chloride, what do you think will be the Vant Hoff factor of calcium chloride? It will be 3, because you have here you are going to have 2 chloride ions and 1 calcium ion. That is something of this nature. You are going to have this and this. you're going to have this. So 2 chloride ions are completely separated, 1 calcium ion is completely separated. So total of ions here is 3. So the Vant Hoff factor for calcium chloride for this one, I is 3. For a salt like this one, ion 3 chloride, the Vant Hoff factor is 4. Class, can you tell me reason? Look at it here now. Here you are going to have 1 ion, 3 ion, and 3 chloride ions. You see? So 1, 3, so 1 plus 3 is equals to 4. So the Vant Hoff factor for this will be what? 4. Okay? In case you ask that. So that is it. If you have any question, you can drop it in the comment box. I will see your question, I will answer your question, all your questions, no matter how strong they are. By God's grace, we are going to answer all of them. Right?